The relative age relationships that we see in rocks allow us to recognize geologic events in a historic sequence through time. But knowing only the order of events is a bit unsatisfying. Without the ability to measure the absolute age of these rocks, it's impossible to fully understand Earth history. And without a calibration of geologic time, we can't study the rates of geologic change that are used to make forecasts about future events. Scientific discovery is often born of chance events coupled with keen perception. In the late 19th century, Madame Marie Curie discovered that when certain types of rocks were stored in the same drawer overnight with undeveloped photographic film, the film was exposed. This chance event led to the discovery of radioactivity. In this process, certain types of atoms spontaneously disintegrate or decay. The decay is random, but it proceeds at a constant rate through time for each particular type of atom, or isotope. Because many different types of rocks contain radioactive isotopes, Ernest Rutherford reasoned in 1905 that the uniform rate of radioactive decay could be used to measure geologic time. From this realization came the eventual development of techniques to measure the absolute age of geologic materials. Now, for example, not only do we know that the dinosaurs disappeared in a global mass extinction, we know it happened 64 million years ago.
Most elements are composed of isotopes, atoms with similar atomic structure, though a slightly different mass. Some isotopes are radioactive and therefore unstable. This instability causes the atoms to radiate energy, some of it in the form of electrically charged particles. This radiation gradually causes the atom to disintegrate or decay over time, transforming the original radioactive isotope, or parent, into a stable isotope, known as a daughter product. We call this process radioactive decay. The sand in the upper half of this hourglass can be thought of as a parent isotope. The sand accumulating in the lower half is its daughter product. With time, more and more parent isotope radioactively decays into daughter isotope, and the proportion of parent to daughter changes to show how much time has elapsed. By measuring the fraction of parent to daughter sand, this time can be determined. This is how radioactive dating works, only much more slowly. The most familiar example is radiocarbon dating. The carbon in air and water is made up of 3 different isotopes. One of these, carbon-14, is radioactive. Carbon-14 in air is absorbed by living plants and animals as they take in air from the atmosphere. When the organism dies, it stops taking in any new carbon, and the amount of carbon-14 inside it gradually decreases as it undergoes radioactive decay. Over time, the fraction of parent to daughter isotopes changes and indicates how long ago the organism died. The rate of decay of any radioisotope is measured in terms of its half-life, the period of time required for half of the parent atoms to decay into daughter atoms. The half-life of carbon, for example 14, is 5,730 years. When determining the age of rocks, geologists often use the carbon-14 that is preserved in charred wood that has been buried by sediment, lava, or volcanic ash. If half of the carbon-14 in a sample has decayed, geologists conclude that it must be 5,730 years old. If half of the remaining carbon-14 were to decay, another half-life would elapse. The sample would be 2 times 5,730, or 11,460 years old, and so on. Most methods of radioactive age dating are accurate for about 5 half-lives. Beyond that, the amount of the parent isotope is too small to permit accurate measurement. So the carbon-14 method is only reliable for dating things back about 28,000 years. To date rocks that are millions or even billions of years old, geologists must work with radioactive isotopes that have much longer half-lives. Uranium-235, for example, makes an excellent geologic clock for old rocks because it takes 713 million years for half of it to decay into lead-207. By measuring and comparing the relative amounts of these two isotopes in a rock, it is possible to figure out its age, even if the rock is several billion years old. In order to determine the age of a rock, it must be carefully processed in order to separate out the necessary chemical elements. Once the elements are separated, they are analyzed in a mass spectrometer. The mass spectrometer separates the different atoms in the sample and measures the mass and relative abundance of individual isotopes. The fraction of the parent and the daughter isotopes can then be determined, and it is this fraction which tells us the age of the rock.
Minerals which contain radioactive isotopes act like tiny clocks inside of rocks, clocks which are reset when a rock is formed or metamorphosed. Before geologists learned to measure the absolute ages of rocks using radioactive isotopes, they could only establish relative ages using the common sense logic of superposition, original horizontality, and cross-cutting relationships. They knew that one rock formed before another, but never how old the rocks actually were. The reliability and accuracy of radiometric age dating is truly impressive. The results of over half a century of radiometric age dating studies are entirely consistent with the relative age relationships developed by early geologists. So the science of geology has given us two ways to understand Earth history. First, we determine the relative age of rock formations and geologic structures, and then use these ages to construct a historic sequence of events through time. Then, by applying radiometric age dating techniques, we determine the absolute timing of these events and measure the rates of geologic change as well. So not only does our study of geologic time allow us to understand Earth's past, it gives us a historic framework and the tools for predicting the planet's future.